Hello, welcome back. Today we'll look at derivation of Henderson-Hasselbalch equation, which is something that gives you uh, the pH of a buffer, which is pH is equal to pKa plus log to the base 10 of typically salt, concentration of salt by concentration of acid. Now, this concentration of salt is nothing but the concentration of the conjugate base you would take, and the acid would be your weak organic acid. Keep in mind that when an acid dissociates, we're talking about a reversible dissociation of weak acids. It dissociates into proton and the conjugate base. Okay. In this case, this particular species that you get from ionization of the weak acid, that is conjugate base because it can accept a proton. Okay, this is simply the definition of concepts of acids and bases, okay, as per Bronsted-Lowry concept. But what we'll do is we'll quickly take a look at how do you get to this equation for pH of a buffer, okay, which is pH is equal to pKa, okay, plus log to the base 10 of concentration of conjugate base, or nothing but acid, sorry, the one that comes out of ionization of acid, concentration of salt by concentration of acid. We'll look at that. How do we arrive to this equation? Okay. Please do keep in mind that there is another video I've posted in the past which describes the importance of pK when it comes to choosing the right weak acid or weak base for making buffers. Please have a look at that. It's very informative in terms of helping you understand what is the importance of this. Okay, we'll straight away get started with this. Let's just look at dissociation of an acid. Okay, weak acid dissociates to protons plus the conjugate base. Okay, now if you were to write the dissociation constant for that, dissociation constant would be product of concentration of the protons, okay, product of concentration of the protons one second, okay, product of the concentration of protons into concentration of conjugate base divided by unionized acid. Okay, now what we'll do is we'll rearrange such that we take the protons to the left hand side. Okay, but in doing so, concentration of protons would be equal to Ka into Ha divided by A minus. It's as simple as that. Okay, now what we'll do is we'll take log on either sides. Okay, take log on either sides. So log H plus is equal to log of Ka into Ha by A minus. Okay, by A minus. Now, if you know anything about log xy is always equal to, let's say, like we'll write it down here, okay, somewhere. Log x into y is equal to log of x plus log of y. By that logic, this would be here log H plus is equal to log Ka plus log Ha by A minus. Okay, it's as simple as that. Now we'll take negative on both the sides. Okay, In doing so, we'll get, I'll just write this equation at the top. Okay. We'll move over from that equation. I'll just erase whatever is at the top. We'll move from this here. Okay. We'll take negative on both the sides. We get negative log of proton concentration is equal to negative log to the base 10. I mean, everything is base 10. You've got to keep that in mind anyways. Okay. Of negative log of Ka minus log of HA by A minus. Okay. Now we know one thing, negative log of H plus is nothing but pH, that we know, is equal to, what is negative log of Ka? Negative log of Ka is nothing but pKa minus log to the base 10 of concentration of acid by conjugate base. Okay. Now, if you know again anything about log A by B would be negative log B by A. You can take the reciprocal and then put a minus. So we have a minus sign already here. Okay. So we'll take reciprocal value of this and make it plus. Okay. So pH is equal to pK plus log to the base 10 of conjugate base by acid. Okay. This is the Henderson-Hasselbalch equation. This is the Henderson-Hasselbalch equation, and we have arrived at the Henderson-Hasselbalch equation. If you prepare a buffer using this equation, you'll also see that you have prepared the buffer. So pH for that buffer would be set, therefore constant. pK of any acid is constant. So truly, what does the pH of a buffer depend on? The pK of the acid as well as the relative concentrations of the salt and the acid. So for a given buffer, pH will be constant, pK will be constant. Therefore, it's just the ratio of salt by acid. Therefore, when you take a buffer and dilute it, the pH is not going to change because the concentration of salt and acid are going to get diluted equally. And that's the reason why this I've already discussed in my previous video. You can have a look at it. The pH of a buffer doesn't change when you moderately dilute the buffer. But what we've done in this video is we've looked at how do you get to the equation that is pH is equal to pKa plus log to the base 10 of salt concentration by acid concentration. Okay. This is the equation for pH of a buffer, which goes by the term Henderson-Hasselbalch equation. You looked at its derivation now. In another video that I'll post soon, you will see how you will use this equation to determine the concentration of salt and acid for preparing, let's say, phosphate buffer, pH 7.3 or whatever at 100 millimolar. Another variable that will be invariably important is the volume. So let's prepare it for 250 ml or something like that. Okay. So that we will look at a little while later in another video. But I hope this video was helpful in understanding how do you arrive at Henderson-Hasselbalch equation, which is going to be useful for determining the pH of a buffer when you know the concentration of salt and acid, or when you know what pH you want to prepare. You can always determine the amount of salt and amount of acid that has to be dissolved for a certain volume to prepare a buffer for a certain pH. Okay. If you like this video, please subscribe to my channel. It will only encourage me to make even more videos. Thank you so much.